to the first set of notes in our final unit. Our final unit is sequence and series. So we're going to start with talking about sequences. So the first question we have to ask ourselves is, what is a sequence? And a sequence is an enumerated collection of objects in which repetitions are allowed and order does matter. So essentially, it's just a list of numbers that have a pattern that you can calculate and find. Nothing really special. So I got 4 examples here. The first one, the pattern is pretty easy to see. 1, 4, 7, you're just adding 3. The second one, you go 1, 2, 4, 8, so this is times 2. The third one is a little bit different. 1, 4, 9, 16. All you're going to be doing is consecutive squares. So this is consecutive squares. And then the last one's a little bit unique. So this is 1, 1, 2, 3, 5, 8, 13, 21, 34. It's called the Fibonacci sequence. So this sequence is defined by the sum of the first 2 terms makes the third term. So sum of last 2 terms gives the next. This one's a cool sequence. The big reason why we're doing sequence and series as a chapter is to introduce us to a bunch of different notation. So our first type of notation is this idea of the terms of a sequence and how we label them. So another way of defining a sequence is to say that a sequence is a function whose domain is the set of positive integers. Thus, it makes sense to use subscript notation to represent the terms of a sequence as shown in the table. So the first term we say is a sub 1. The second term, a sub 2. Third term, a sub 3. And so on and so forth until you get to the nth term. Okay, so this is the a sub n term. So that's just the nth term, and that could be anything you want. You plug in a value for n, let's say 32, then the a sub nth term is going to be a sub 32. And then this notation gets really, really nice because then we can talk about the values around the nth term. So a sub n, the term after that, is going to be a sub n plus 1. Term before it, a sub n minus 1. And then the term before it, so 2 terms away, would be a sub n minus 2. And this notation gets really, really nice in letting us talk about things that we don't actually know. So we can talk about sequences in general as opposed to in specifics. So that's really important in mathematics. And we're going to see this once we get to our proof by induction section at the end. So one little note before we move on is that we're always going to start with a sub 1. Okay, so our first term is always going to be n equals 1. If you start at n equals 0, it messes everything up, but you could. So you could say a sub 0 is the first term, a sub 1 is the second term, and so on and so forth. It's just kind of a definition switch. But for this, we're going to stick with a sub 1 is the first term. And that's an important note to make. So there's 2 ways to write formulas for our sequences. You can use a recursive formula, and this defines the term in a sequence by relating each term to the 1 or 1s before it, or an explicit formula, where you define the nth term of a sequence in terms of the value of n. Each of them have their uses, and we'll kind of look at an example of both now. So when we describe the sequence as add 3, so in this one here, we're adding 3 each time. We are giving a recursive formula for the sequence. So we're saying add 3. So then the next term, you add 3 to it. Second term is the first term plus 3. The third term is the second term plus 3. Fourth term, third term plus 3, and so on. Thus the nth term is the n minus 1 term, so the one before it, plus 3. and the n plus 1 term is the nth term plus 3. So written out with notation, you would say a sub n is equal to the a sub n minus 1 plus 3. And this gives us a definition here. One thing about recursive formulas is you have to give a starting place. So you have to give a sub 1 or a place to start. So we'd also have to say a sub 1 is equal to 2. If you don't have both of those, the recursive doesn't work because you don't know where to start. For our explicit formula, it's this consecutive squaring. So when you describe this sequence as n squared, we are setting an explicit formula for the sequence. An explicit formula works the same as a function rule. We input a value for n, and the output is the value of the nth term. So using my subscript notation, a sub n is equal to n squared. So this is in terms of n. And then we can look at an example. So a sub 3 is going to equal 3 squared, which is equal to 9. So you can see that it works. Now, the really important thing that you have to remember is that recursive talks about terms as the values you're plugging in, and explicit talks about values of n that you're plugging in. So in one, you're going to plug in past terms to find the next term, and the other one, you're going to plug in values of n. In this sequences section of this chapter, we're going to see two specific types of sequences with specific formulas that you will probably need to remember. The first type is called an arithmetic sequence. So in an arithmetic sequence, the difference between consecutive terms is constant. This difference is called the common difference, and the common difference can be positive or negative. So any sequence that is described by add x or subtract x is an arithmetic sequence. We have two formulas here. One is recursive, where you need a sub 1, and then you define a sub n as the last term plus the common difference. And the other is an explicit formula, where you have a sub n is equal to the first term plus d times n minus 1. You just need to remember this. This is something that you should have ingrained in your mind at some point. So let's go through and try this. Let's write both a recursive and an explicit formula for the arithmetic sequences. I'm going to start with my recursive formula. So start with stating the first term. A sub 1 is 2. Then say the nth term. A sub n is equal to the term before a sub n, so a sub n minus 1, plus the common difference. And in this case, my common difference is 6. Okay. Explicit formulas are a little bit more challenging, but if you know the formula, it's not that hard. Start with a sub n is equal to, and it's a sub 1, so the first term again, which is 2, plus my common difference, which we saw was 6, times n minus 1. And then what I like to do is I like to turn these into an expression that does not have so much going on, so I multiply it out. So this is equal to 2 plus 6n minus 6, which is equal to 6n minus 4. So a sub n is equal to 6n minus 4. The same steps for my next problem. Figure out what your common difference is. Well, the common difference here is minus 3, so d equals negative 3. So I'm going to add negative 3 each time. Be careful with your signs. My first term, a sub 1, is equal to 4. And then my a sub nth term is equal to the term before it, a sub n minus 1 plus negative 3. And really, I could have just written that as minus 3. So you have to be careful of your signs. For my explicit formula, it's the same process. A sub n is equal to 4 minus 3 times n minus 1. And then if I distribute this out, I should see that a sub n is equal to negative 3n plus 7. Now, the reason why we talk about the explicit formula as opposed to the recursive formula, maybe a little bit more, is because it's just like what we've been doing in math for pretty much your entire mathematics career. You're given a function where you can plug in numbers. And that kind of helps us when we want to find a term in a sequence that we don't want to go through and write down all the terms that came before it to get to it. For instance, if I want to find the 32nd term, if I was given a recursive formula, I'd have to write down 31 terms before I got to that one. But if I write an explicit formula first, you can quickly find the 32nd term by just plugging in 32 for n. So let's go through and do this. My common difference is equal to 0.2. Can write a formula then. A sub n is equal to 0.4 plus 0.2 times n minus 1. First term plus common difference times n minus 1. Alright, now to find a sub 32, I just plug 32 in for n. So I got 0.4 plus 0.2 times 32 minus 1, which is approximately 6.6. If you want to know how I got that, I plugged that into a calculator. It was very exciting. I won't show my work. Alright, there's one more idea that I want to talk about before we start talking about geometric sequences, and that's the arithmetic mean. So the mean of any two numbers is the average of the two numbers. So add them together, divide by 2. And we can use this to find missing terms in a sequence. For instance, if I want to find these 3 terms in this sequence, it's really hard to see the common difference here. I can't see what I would be adding each time. But I could go through and use the arithmetic mean to find the number in the middle here. So 2 plus 50 divided by 2. Well, this is just going to be 52 divided by 2, which is 26. So this middle number is 26. And I can use that logic, 2 plus 26, to find this number right here, divided by 2. This is going to be 14. So I know I'm going to be adding 12 each time, which means that this one has to be 38. So you can use mean to find missing elements in a sequence. Now this isn't something that you might see on the IXL assignment, but it is something you might see on a test like the ACT or anything like that. I just figured it'd be nice for you guys to know. Alright, this one's a little bit different. We don't know these terms, and there's no middle term, so it gets very challenging to find them, but we can use the definition of our sequence to do so. I know a sub 1 is the first term. That means the next one is a sub 2, this is a sub 3, this is a sub 4. It'd be really handy if we could figure out the common difference, and we can because we have the first term and the fourth term. And if I have the first term and the fourth term, I know a sub n is going to be equal to a sub 1 plus d times n minus 1. I have 3 of the 4 variables in my equation. 20 is the a sub nth term. Because 20 is the a sub 4th term, n is 4, which means I can plug it in here, and my first term is negative 3. So plugged all in, I get negative 20 is equal to negative 3 plus d times 4 minus 1. Put it all together, I get negative 17 is equal to 3d, or d is equal to negative 17 over 3. Alright, so that's my common difference. And now I can find a sub 2 by adding negative 17 over 3 to a sub 1. So a sub 2 is going to be negative 3 plus negative 17 over 3, which is equal to negative 26 over 3. So this term is negative 26 over 3. And then the next one, a sub 3, is equal to a sub 2, which is negative 26 over 3, plus my common difference, negative 17 over 3. And this is going to be negative 43 over 3. So I used both my explicit formula and the recursive definition to find the missing values. So both are kind of handy. The other type of sequence we're going to talk about is called a geometric sequence. So in a geometric sequence, the ratio between consecutive terms is constant. This ratio is called the common ratio. Common ratio can be positive or negative. Any sequence that is described as multiply by x or divide by x is a geometric sequence. And they have two formulas. The recursive formula, you take the first term, multiply it by the common ratio to get the next term. An explicit formula looks like this. A sub n is equal to a sub 1 times r to the n minus 1. So let's go through and try this. Let's write a recursive and an explicit formula for the geometric sequences. First step is to find r. For this first one, r is 2. So for my recursive formula, I have to say the first term, a sub 1 equals 1, and then I have to say the a sub nth term is equal to 2 times the term before it, which is a sub n minus 1. Explicit formula, I got a sub n is equal to the first term, which is 1, times 2 to the n minus 1. And then I just simplify this to be 2 to the n minus 1. Next problem, I got my first term is 54, common difference is going to be, or not common difference, common ratio is going to be 1/3. So r is equal to 1/3, multiplying by 1/3 each time. Alright, so that means first term, as I said, was 54. And then my next term, a sub n, 54, I wrote 55 for some reason. Let's fix that real quick. So then a sub n is going to be equal to the last term times 1/3. So 1/3 times a sub n minus 1. For my explicit formula, I have a sub n is equal to 54 times 1/3 to the n minus 1. And really, the big reason why we're doing sequences and series is because, like I said, notation, and also this pattern recognition. So you have to be able to recognize patterns pretty quickly. I think you guys will be good at this. I don't think this should be super tricky or challenging because we've been doing this all year. It's just more defined now. I'm writing formulas for them. So you have two formulas so far that you have to remember. The recursive thing you don't really need to remember, you just need to understand. But the explicit formula here and the explicit formula up here. I got two arrows, but you know what I mean. Alright. One last thing I want to talk about, because it might pop up, is called the geometric mean. So the geometric mean of any two numbers is the positive or negative square root of the product of the two numbers. So geometric mean is plus or minus square root product of two numbers. So let's find the missing terms in each of these geometric sequences using the geometric mean, or using our equation like we did last time. So let's find the missing terms of this thing here. Got three terms, it means I'm missing. I can find this one first using geometric mean. So I got the positive and negative square root of 2 times 162, sorry. This is going to be equal to positive and negative square root 324, which is clearly plus or minus 18. Now, because there's a plus or minus, we kind of have to decide. And this is a really important aspect of geometric sequences, in that they can change sign positive to negative depending on whether or not your r value is positive or negative. So let's do kind of a sign test. So if I have a plus, and then something, and then something, and then something, and then a positive, so positive, something, 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 positive, I can go through and figure out what are my signs going to be? What possible signs could I have? Well, let's say my r is positive. So a positive times a positive is positive. A positive times a positive is positive. Positive times a positive is positive. Okay, so if r was positive, all of my values are going to be positive. All right. So let's change it though. What if r was negative? All right, what would happen to my sequence then? Well, a positive times a negative is going to be a negative. And then a negative times a negative is going to be a positive. And then a negative times a positive is going to be a negative. And then a negative times a negative is going to be a positive. So you can see Depending on what r is, will change what our sequence is going to be. But this middle term was always positive, so I just take the positive 18 as my middle term. All right, let's find my other two terms. I do 2 plus 18, take the square root, put a plus minus, not plus, times 18. 2 times 18 is 36, square root of 36 is 6. So plus or minus 6. And as we saw in this last example, these two things here are going to be positive or negative depending on your r value. And we don't know r here, so we have to account for both. So this is going to be plus or minus 6. And my last term is going to be the positive and negative square root of 18 times 162, which is clearly equal to positive and negative 54. So this is plus or minus 54 right here. All right, last problem. Okay. To do this, we use a similar method as before. Label them a sub 1, a sub 2, a sub 3, a sub 4. And if I have the fourth term and the first term, I can use my equation to solve for r. So I know a sub n is equal to a sub 1 times r to the n minus 1. If I have a sub 4 as my a sub nth term, that means that n is 4, a sub n is 21. So negative 21 is equal to my first term, which was negative 3, times r to the 4 minus 1, which is 3. Go through and solve this. I got 7 is equal to r cubed, or r is equal to the cubed root of 7. And to get my next term, I'm just going to use my recursive definition. A sub 2 is going to be equal to the last term, negative 3, times the cubed root of 7. So this is negative 3 cubed roots of 7. To get the next term, a sub 3, this is going to be my last term, negative 3 cubed roots of 7 times the cubed root of 7, or negative 3 times the cubed root of 49. Plug that in up here. And there you go. That's your equation right there. So good luck on the IXL stuff. If you have trouble or issues, let me know, and we can go and figure out what's going on. Thank you very much.